let me still go through questions on how to identify ordinary differential equations and how to verify that a given function is a solution of a differential equation. Right. So here is an example. So we are supposed to figure out which of these are ordinary differential equations. So let me first delete those that are definitely not ordinary differential equations. So like the last one, notice that there is no differential here. This is not an ordinary differential equation. So this is a one parametric family of curves. So one parametric because we have a parameter c, right? So this is a one parametric family of functions. That often appears as a solution of an ordinary differential equation. But of course, the family itself is not a differential equation. Okay, so this is not a differential equation. Then there is another item here that doesn't have a differential. It's this one. So this is not a differential equation at all because there is no differential. This is what is called a functional equation, right? So it relates the values of an unknown function at different points. So here we have points t and u, and here is the relation that y evaluated at t plus u equals well, blah blah blah. So this is called a functional equation. All right, so the rest of these, they have some differentials. So let's go through them one by one. Let me first rule out this option. The reason is because here we have partial derivatives of the unknown function y with respect to t and u. So it means that the unknown function y is a function of two variables, t and u, where t and u are independent variables. And the equation here, it involves partial derivatives of the unknown function. So such an equation is called a partial differential equation, or PDE. So this is a partial differential equation. So remember that an ordinary differential equation, it involves derivatives, consecutive derivatives of an unknown function, but with respect to just one independent variable. So then if you look at the third option, we shall rule it out too, because notice that here y prime is evaluated not at the point t, but rather at the point t plus 0.4. Right? So when y prime and y are evaluated at different points, not at the same point across all the equation, this is not ordinary differential equation. So this is called a delay differential equation. Delay differential equation. Differential equation. Okay, so let us look at the fourth option. Well, the fourth option, it has a differential. It has t, but notice that it does not have the unknown function, right? So you can just explicitly differentiate the left-hand side. When you differentiate the left-hand side explicitly, dt of e to the minus 2ct squared, you get minus 2t times e to the minus t squared equals 0.4t. And this is, of course, it's not a differential equation. It's just an ordinary algebraic equation. It's just the way it is written, it has this differential, but there is no unknown function here. So which means this is really just a usual algebraic equation like those that you learned in secondary school. Okay? Well, then if you look at the first option, then this is actually an ordinary differential equation because it relates y prime, y, and t. And both y prime and y are evaluated at t. Well, which we can see by from the fact that the point at which they are evaluated is not indicated. So when it is not indicated, it means that they are all evaluated at t, and t is the independent variable, right? So this is an ordinary differential equation. Same concerns the second last option, only here y prime and y triple prime appear, so which means that this is also an ordinary differential equation, but its order is 3 rather than 1. Well, so the remaining equation is y prime minus y equals d over dy of y squared. Well, so let me rewrite it. So the left-hand side is y prime minus y, and the right-hand side, notice that we can just explicitly calculate it. So we just need to take this expression and differentiate it with respect to y. Right? So what are we going to get? So dy squared over dy is 2y times e to the t minus sine y plus y squared times the derivative of e to the t minus sine y. E to the t is a constant, so we can, with respect to y is a constant, so we can take it out. And then we should differentiate e to the minus sine y. Then the derivative is going to be e to the minus sine y times the derivative of minus sine y, which is minus cosine y, minus cosine y. Well, but my point being is that now it is just an explicit expression in terms of t and y, and the whole thing is just an ordinary differential equation too. Even though it contains the partial derivative, but it's not a partial derivative of the unknown function. The unknown function y, it only involves an ordinary derivative here. So which means it is an ordinary differential equation. All right, so how do we verify that a given function is a solution of the given differential equation? So we just substituted as y into the equation and see if it turns the equation into a correct equality. And so if y is e to the sine t, then y prime equals the derivative of e to the sine t is e to the sine t times the derivative of sine t, which is cosine t. Okay, so then the left-hand side of our differential equation is y prime squared. So y prime squared is e to the sine t cos t squared plus sine squared t times y squared. Y is e to the sine t, so e to the sine t squared. Let me continue. Now e to the sine t squared is e to the 2 sine t times cosine squared t plus e to the sine t squared, again e to the 2 sine t times sine squared t equals, so e to the 2 sine t can be factored out. Here we have cosine squared t plus sine squared t, and this is just 1. Cosine squared t plus sine squared t is 1, which equals to the e to the 2 sine t, and this is exactly the right hand side. So since the left hand side equals the right hand side, it means that it is indeed a solution of this differential equation. So, and this is how you verify that a given function is a solution of a given ordinary differential equation. All right, and a small extra example on modeling, but throughout the semester we're going to see many more examples of modeling, so I hope this is not too confusing. But anyway, of course, it's not going to make any harm if I give you one more example. So a pond initially contains 1 million gallons of water and an unknown amount of undesirable chemical. Right? So let me write that y of t is this unknown amount of undesirable chemical. So this is our chemical. Well, so let's write water containing 0.0 gram of this chemical per gallon, whatever it means. So the amount of chemical is measured in grams. So in grams. So it flows into the point at a certain rate, and then the mixture flows out at the same rate, and so on and so forth. So the question is to write a differential equation describing the process. So let's write down a differential equation. Means that we should really work with y prime. So y prime is the rate of change of this undesirable chemical. So the rate of change, it adds from two components. So the rate in, so how much of that chemical flows in, plus rate out. So how much of that chemical flows out. So how do we compute the rate in, the inflow of this chemical? And so what we should take is we take the flow in times concentration of our chemical in the inflow. Well, the rate out is really should be taken with a negative sign, so I will write negative here. Well, because rate in means the amount is increasing, and the rate out means the amount is decreasing. And so I will write the flow out, whatever flow is, times the concentration of our chemical in the flow out. Concentration out. Okay. Then I'm going to continue. What is the inflow? So the inflow is given is 300 gallons per minute. So 300 gallons per minute. What is the concentration of the chemical in the inflow of water? It is given in the question. It is 0.01 gram, 0.01 gram of this chemical per gallon. So it's gram per gallon. Minus, what is flow out? Well, the mixture flows out at the same rate. So the flow out is at the same rate, so this is also 300 gallons per minute. What is the concentration of this chemical in the outflow? So assuming that the chemical is uniformly distributed throughout the pond, so it means that the concentration in the outflow is the same as the concentration of the chemical in the whole pond. And the concentration of the chemical in the whole pond is, of course, the total amount of chemical divided by the total volume of the pond. And the total amount of chemical is Y grams, and the total volume of the pond is 1 million gallons. So 1 million gallons. So I will write 10 to the 6 gallons. Now notice that the units are actually correct because gallons and gallons cancel out here, gallons and gallons cancel out here. So the resulting units of this are going to be grams over minute, which makes sense because this is the rate of change. So if the initial quantity is measured in grams and time is measured in minutes, then the rate of change should be measured in grams per minute. Well, and then we just need to write it down. So 300 times 0.01 is 3. Yeah, that's all. Minus 300 times 10 to the minus 6 is 3 times 10 to the minus 4 y. And this is the answer. So y prime equals 3 minus 3